Hi, Rajesh Kumar from AIC. Last time we have discussed about the structural isomerism. Today we are going to further proceed in this chapter. This time we are going to discuss about the stereoisomerism. A stereo means a space. It is a type of isomerism in which the molecule differs in respect of the arrangement of the group or atoms in three-dimensional space. That is, they differ in respect of their configuration, not in their constitution. A stereoisomerism is further of the following three types. One is conformational isomerism, geometrical isomerism, and optical isomerism. One by one, we are going to today discuss each one in detail here. First, it is your conformational isomerism. It is also called rotational isomerism. This type of isomerism is observed in the molecule having single bond, that is of the sigma bond there. In this type of molecules, the isomers differs in respect of arrangement of the group or atom due to the rotation of group or atom in three-dimensional space around the carbon-carbon single bond. So here the group or atom differs in respect of rotation of carbon-carbon single bond. It means there is a rotation is being caused between the carbon-carbon single bond. First, this rotation is not completely free. Rather, 1 to 20 kilojoule of energy barrier is involved to check this very rotation. But there is some torsional effect or torsal strain is effective due to the repulsive interaction with the bonded pair of electrons that make it to cause the rotate there. Due to this rotation, whatever the structural changes in three-dimensional space takes place, that is called conformational isomerism. This type of isomerism is observed in alkane and cycloalkane-like molecules. Okay, so now we are going to learn how to represent this conformational isomerism. This conformational isomerism can be represented by following two ways. One is called Sawhorse method. Another is Newman method. In Sawhorse method, the molecule is observed across its axis like this one. But in Sawhorse method, molecule is viewed from the front across its axis like this one. This direction. Okay. So if it is here, this rotation is caused like this way. It could be another structure could be here like this way. So due to rotation, the arrangement has been changed. Here it can view like this one. This dot is your front last one carbon, and this circle is going to represent your front carbon. So it is going to represent it like this one, and it is also going to represent it like this way. Like this way. So in Sawhorse method, the molecule is viewed from the front, but in Sawhorse method, the molecule is viewed from the across the bond from the side. But in Newman method, molecule is observed from the front along the side, from the front. Now we will discuss the conformational isomerism in butane, and we will represent all the stages of the conformational isomerism by the Newman projection or Newman method. Come on here, see the butane. CH3, CH2, CH2, CH3. This is your butane. We are going to represent the conformational isomerism along this very bond here. Okay. So, in numerical projection, the front carbon is represented by a big circle and dot by the last one viewed from the front of this one. And this bond is of front carbon one and this bond is of backward one. Okay, this is your CH3 and CH3. Both bulky groups are present here, side to side, and bond is nearest approach. So due to this reason, both bulky groups are present near about each other. That's why there is a steric repulsion or a strain is possible between the both bulky groups. And there is also a torsional strain between the bonded pair and bonded pair of electrons possible there. So due to this repulsive attraction, this bond is going to rotate around electron, and due to rotation, both group keep themselves or try to keep themselves away from each other so that they should have maximum stability is possible here. The initial stage where the both bulky group is going to superimpose to each other or nearest to each other, this is called full eclipse condition. Now, both bulky group are little away from each other. This is called skew form. And still the repulsive interaction is going on. Due to repulsion, both bulky group or all the groups repel to each other, and this time again see one bulky group and one smaller groups are going to be superimposed in this condition. This condition is called eclipse condition. Still the repulsive interaction is going on, torsional strain is still effective, and also to a certain extent the steric strain is also effective. Due to this reason, again the rotation around the carbon and carbon bond is going on. Due to this rotation, both bulky groups keep themselves away from each other by its maximum distance. Due to this reason, both bulky groups are away from each other due to rotational reason, due to the torsional strain, due to the steric strain, occupy the maximum distance from each other and keep themselves stable there. So this stage is called anti-stage. So in these 3-4 stages, the conformational isomerism is represented in butane by the Newman projection. Now we can discuss about the stability order of each stage there. So a stability of anti is the most stable one because bulky groups are away from each other at its maximum distance, and that's why the energy of the system is the minimum here. That's why it is most stable one. Then followed by skewed. No bond is being eclipsed here. Repulsive interaction is effective, but not to the as extent as the others one, like full eclipsed and eclipsed one. That's why it is more stable there than eclipsed and full eclipsed. Another one is eclipsed one, because bulky group and smaller groups are going to be superimposed to each other, nearest to each other. A steric effect as well as torsional effect is effective there. It makes it little unstable or unstable. And again here it is full eclipsed. It is least stable because bulky groups are going to be superimposed to each other, and both all bulky groups are nearest to each approach, and that's why steric effect is very much predominant there. That's why it is least stable there in this way. So in the full eclipse there is a maximum energy and least stability, while in the anti-form there is a minimum energy and maximum stability is possible there. So in this way we can represent the conformational isomerism in butane or in any other along the carbon-carbon single bond is there. Now we will discuss about the conformational isomerism in cycloalkanes. So conformational of cycloalkane. Cycloalkane. Now it is very important to discuss what the stability of the cycloalkane compound. The cycloalkane compounds are considered least stable. Especially in case of 3 and 4 member ring, it is considered least stable rather than 5 and 6 member ring. There is a concept named as bare strain theory. According to this theory, 5 member ring is most stable one, but now today it has been proved that 6 member ring is the most stable one, because almost all bonds are strain free there in cyclohexane. Now question arises, why the 3 member or 4 member ring in cycloalkanes are less stable? Answer is only here due to the angular strain. In case of cycloalkane, there is angle variation from the expected one. Take the example of cyclopropane. Cyclopropane is a 3 member ring structure. Three-member ring structure. So the bond angle is here 60 degree. The expected bond angle was 109 degree angle, but its bond angle is 60 degree, much less than the from the expected one. That's why this molecule is said to be least stable there. But as the bond angle increases, means as the size of the cycle ring increases, bond angle increases, and bond angle increases, so it will try to achieve the that bond angle that should be available in sp3 hybridized carbon, that could be 109 degree angle. So with the increase of number of member in the ring, the bond angle increases, so its stability increases, but it is not very effective beyond 5 or 6 member ring, because due to increase in bond angle, its bond angle also deviates from the expected one. As in case of 7 member ring or 8 member ring, the bond angle is very more than the 109 degree what was the expected one, while in case of 3 or 4 member ring, it is very less than the from the expected one. But in 5 member ring, the bond angle is up to the expected one, that is it is 108 degree, while in sp3 hybridized carbon it should be 109 degree, very near about the expected bond angle. That's why Baer said that 5 member ring is most stable one, but this is not true, because some bonds are also eclipsed there. How can we determine the bond angle in a cyclic ring structure? Now question is this one. The bond angle alpha is equal to 180 minus 360 upon n, where n is the number of members of ring that is of carbon atom, So take the example of 3 member ring. If n is equal to 3, then alpha is equal to 108 minus 360 upon 3 is equal to 180 minus 120 is equal to 60 degree. So in 3-member ring, the bond angle is 60 degree. Similarly, in 5-member ring, where n is equal to 5, alpha could be 180 minus 360 divided by 5. It will be 180 minus 72 is equal to 108 degree. So in case of 5-member ring, the bond angle is 108 degree from the very near to the expected one, that is 109 degree. That's why 5-member ring was considered by Baer is most stable one. But he forgot to explain that some angles were or some bonds were strained or not, eclipsed or not. Hello, okay. Last time we have discussed about the stability of the cyclic structure or cyclic ring structure. That very time we have discussed about the stability of the ring structure decreases due to the angular strain. This is known as Baer strain theory. For the stability of cyclic structure, not only the angular strain is responsible, but also some other strains are also responsible. The cyclic structure bend and twisted in such a manner that the molecule gets the maximum stability. In a cyclic structure, there are following 3 types of strains are effective. One is called angular strain, this strain is caused due to a deviation of the angle from the expected one. As for example, if it is 6-member ring structure, this angle is around 120 degree, but this carbon is in sp3 hybridization, this angle should be of 109 degree. That's why it is going to deviate here from the expected one. This angle has been increased from the expected one. That's why the strain is going to be imposed there and it makes molecule unstable. If it is of 3-member, this carbon is still it is in sp3 hybridization, bond angle should be 109 degree 28 minutes, but this angle is 60 degree. So this angle is going to be deviate due to decrease in angle from the expected one. This makes the molecule unstable. Baer also made a mistake there. He considered all the cyclic structure is a planar structure, but this is not true. If there is an internal strain, the molecule could be a planar structure, but if there is an external strain is going to impose over the cyclic structure, the molecule is not a planar structure, rather it will be bended and twisted in different manner to make the molecule stable. This is one of the strains. Another strain is torsional strain. The strain caused due to the repulsive interaction between the bonded pair and bonded pair of electrons. Take this for example here. This bond pair of electrons are very near to each other. So there is a repulsive interaction between this bonded pair of electron and this bonded pair of electron. That's why the molecule is said to be unstable here. If it is going to be twisted or bended or rotated along the axis here, like this manner. Now this time each bond pair is as of maximum distance from each other, this molecule more stable. Okay, and another strain is here, a steric strain. The strain is caused due to the repulsive interaction between the groups or atoms. Take the example here. If two bulky groups are nearest to each other, there is a repulsive interaction between these two bulky groups makes the molecule unstable. So molecule is twisted and bended in such a manner that three strains, the three mentioned strains become diffused there, neutralized there, and so that molecule become more stable. And again, such a geometry that makes this molecule more stable there, minimum energy is possible there. Now come on the conformational isomerism is cyclohexane. In case of cyclohexane, this cyclic structure is considered most stable one because all bonds are considered strain free, and this cyclohexane structure exists in two conformations and both are interconvertible to each other. This is called chair form. This chair form, one chair form get converted to another. This is called ring flip. So chair conformation is the most stable conformation, and one chair form or one chair conformation convert into another. This process is said to be the ring flip. It is little complicated one. I am going to discuss each and every stage of this one. Cyclohexane. One chair form get converted to another by following this process. It get first converted into the half chair, then twisted board, and then board. Similarly, this board get converted into another twisted one, another half chair, and another half chair get converted into the another form of the chair model. So this is called ring flip. In a ring flip, this chair model get converted into another chair model via board model and half chair and twisted board model. In this ring flip, the different stages and different conformations have different stability as well as different energy. Half chair has the maximum energy, so its stability is the least one, while board model has little stability or less stability than ring model chair model, because one of the bond, that is called flat point or flat peak point bond, is eclipsed one. That's why it is less stable. So a stability order in case of conformational isomerism of cyclohexane is chair model followed by twisted board, followed by boat model, followed by half chair. And this conversion is called ring flip. So one form get converted to another in chair model. This is called ring flip. There is another form of the conformational isomerism observed in amine, that is called amine inversion. In case of amine inversion, non-bonded pair of electron always turns inside out or upside down. That makes another conformational isomerism. There also energy is involved around 1 to 20 kilojoule of there. This is all about your conformational isomerism. Thank you.